Okay, moving on with our types of crystalline solids. By the way, welcome to video 3 of Unit 10, Liquids and Solids. So we were talking about how the noble gas elements are attracted to each other. They're not necessarily bonded, but they're attracted, and it's because of these London dispersion forces. Why would they be so special? Why do they attract to each other that much more than other things? Well, because they're so big. And they have so many electrons surrounding them in their outer shells. Of course, those electrons are going to move around a lot and have a greater chance of attracting one another by being in weird places. So keep that in mind as something that can occur with those noble gases. The clicker's not working. Here we go. So here's an example of our 3 types of crystalline solids. On the left here, we have that diamond, right? And our diamond would fall into that network solid. In the middle, we have sodium chloride. What would that be like? Well, that's also going to be a type of solid here that's ionic. So just like number 1, we have our ionic solid. And then lastly, we had ice. The way ice is attracted to one another is by that hydrogen bonding. Okay, so that falls under that atomic type of crystalline solid. How about classifying some of those solids? This might help you out. So they're classified as metallic if they're metal atoms and we consider them to be delocalized, or a sea of electrons. They're considered network if they're nonmetals and they have those directional covalent that go to really big molecules. And their group A means group 18. That's going to be if you have noble gases. And then we have our molecular solids, which would be between these molecules that have dipole-dipole London dispersion forces, like hydrofluoric acid or hydrochloric acid, or something that's between hydrogen and a really electronegative element. And lastly, ionic solids are going to be between those ionic molecules. Okay, so how about those metals? We already know all this stuff. They conduct, they're malleable, they're ductile, and we think of them as packed together atoms of the same sort with a sea of electrons. Well, we have to expand our thinking on that. What we call one of the models is the closest packing model. This assumes that all these metal atoms are uniform hard spheres. Is that true? No. Remember what a model is. It's a way to think of something. We also assume that they're packed in these layers. Well, we have to talk about the way these layers are packed together. So the one that makes the closest or most tightly packed arrangement we call ABA packing. The reason it's called this is because the second layer is like the first, but it's displaced so that it goes into the dimple of the last layer. I think of this kind of like Legos, how they fit perfectly into one another. Well, these are like identical Legos on top of each other. They just move back and forth one space each time. And this is a good picture of how they end up laid out. So each of the layers is identical. They're just moving back and forth each time to fit the dimple of the other layer. The most tightly packed, easiest to remember. Then we have what we call ABC packing. In this case, our third layer is one step over. So originally in our ABA packing, our third layer was directly on top of our first layer. And our fourth layer was directly on top of our second. And if we kept going...
Office, will you contact the front office, please? If you're in the building, please contact the front office, Ms. Bill.
Okay, so the way they're arranged are directly over top of each other, every other layer. But in ABC, it's like 3 layers. So layer 1 is different from 2, is different from 3, but then we start over again with layer A, or layer 1, being identical to the first one. The fourth layer goes back to being like the first, in other words. So here's just an example of that first packing, that ABA packing, where the third layer was just like the first. And it shows a couple different views. Now if we cut out that unit cell we talked about, this is what it would look like. Big one in the middle, quarters in the corners. Here's the second one we talked about, where it takes until the fourth layer for it to be similar with the first layer. And you can see how that would look differently if we zoomed in on it. So each sphere in both of these packing methods, and you see it worded different ways, this just means the type of packing. So this one said face-centered cubic, and this one said hexagonal. It's really referring to those two types. So essentially here what we're saying is that nearest sphere, that guy in the middle, he has 12 neighbors. So there are these 6 around him, 3 below and 3 above, that all surround that guy in the middle. He's got 12 protecting him. That's what makes metals strong, malleable, and ductile, because they have this close-knit, tight neighborhood, I guess you could call it. And we can calculate the number of spheres that would be in one little unit cell if we think about how much of an atom is there. So in this one, we have these half atoms, and there's one here, one on top, 2 in the back, and 1 on the bottom if I were to rotate this around 3D. And that would give me 6 of them. Then I have these little, essentially eighth of an atom, I guess you could say. We have 1 on each corner, so we have 8 of those. If we add all those up, it would be like packing 4 cells closely together. And that's showing you, just like that last picture where we had the 12 neighbors, what it would look like if we zoomed in on one unit cell. Now we're talking about face-centered unit cells. In other words, it's like we're looking at the face of our atoms here. We're not looking at one circular atom in the middle. So when we talk about those guys, there is a way to calculate the amount of atoms that are within that cell. And we don't really have to know how to calculate it, but we have to know that we're essentially counting up every one of those little guys inside one unit cell in order to determine the total number and to get an accurate description of that cell. And this is just showing you a picture of where we came up with all these numbers. Well, over here we're talking about the number of radii, and we're talking over here about the distance between one point and the other on our triangle. So it's all helping us calculate essentially how many units we have inside our cell. Okay, so here's an example. I'm going to put this up on Canvas as well, so if you really want to try and calculate these out, but we actually don't have to know how to do this, we just have to understand the types. And this is showing a way to calculate density, and all we did here was we plugged in the radius. We're trying to solve for d, and then we have to cube d because it's a cube, and converted our picometers over to centimeters. And then we converted it all to mass because it said it was silver. So we went from the number of atoms in it to the number of grams to the number of moles in order to get out grams. This, if it were reversed, would be the way you're used to seeing it. Atoms would be on the bottom next, moles on top, and then moles on the bottom and grams on top. I know this is a little confusing, so don't stress if you're not getting that. And lastly, we plugged in our mass and volume in order to get our overall density. And that's how we calculate density of metal. Okay, so this is important. We are going to talk about the different bonding models for metals. We're used to the electron C model. Hey, there's a bunch of electrons moving around as if they're in an ocean. But there's another one that we call the band model. And what the electron C model says is just like we're used to. There's a bunch of positives in the middle, negatives floating around, and it allows these guys to be malleable and ductile. But what the band model says is electrons actually travel around this metal crystal in specific orbitals. And they have to do with the number of orbitals, the fact that it turns into a d orbital, and all those things we know about electron configuration. When a bunch of them are together, those molecular orbitals kind of mash together sort of like hybridization, and they result in all these bands. Now the electrons can move from one to another, and that's what allows conduction of electricity. In this case, we call them conduction bands. Here's an example. If we only had two orbitals interacting, they'd be pretty far apart. But as we get 4, they start to squish together, 16, and then we get up all the way to Avogadro's number. Think of all those atoms packed together within 1 mole of a metal. This is what makes it look like a C. But according to the molecular orbital model, they're saying the C is actually a bunch of squished together atomic orbitals that are allowing the electrons to flow between them. Both sort of make sense based on the knowledge we have about metals. Here's an example of magnesium. So what they're showing here is separate magnesium atoms, and their bands of where electrons can move are squished between them all. Well, if those electrons are bouncing between all these guys, that makes it really easy to conduct electricity, to be malleable, to be ductile. This is a model that makes sense. So it's showing us our bands, which is the same as the molecular orbitals. Okay, so how about alloys? Do you remember what an alloy is? It's a mixture. We mix them to try and get some really good stuff out that's better than the originals. But we do have 2 types. One is a substitutional alloy. That's like subbing someone out in a game. You take one person out, you put another one in. Well, what we're doing is we're taking some metal out and putting another type of metal in, and it has to be a similar size. Then there are what we call interstitial alloys. These are like filling in those little holes that are occurring naturally between the atoms. So 2 different types here. Of course, if we're filling in holes, these must be smaller atoms. Here's an example. On top here we have brass. It's substitutional. Copper and zinc are very similar in size. We just took a couple coppers out, plugged some zincs in. Now we have brass. Makes it much stronger than copper is, and keeps the same sort of copper coloring, but we have that zinc in there to help strengthen it. Then we have steel, a bunch of iron stacked up, but in between the iron we put these little pieces of carbon in. That really not only strengthens it, but it gives it some properties that other metals don't have as well. So steel is one of those that the little pieces fill in, so it's considered interstitial alloy. So how about those network solids we talked about? They contain these strong directional bonds, and you can think of them as this giant molecule, just like a diamond. Well, diamonds are actually brittle, even though we don't think of them as being brittle. They aren't flexible, so they're usually bad conductors of heat and electricity as well. You can almost think of them as ionic compounds. They have high melting and boiling points. They often have carbon and silicon, but sometimes they are actually covalent. They're just really strong and they act like ionic bonds.
In this animation, we will be visualizing the diamond form of carbon. Carbon forms 4 single bonds using sp3 hybridization. Each carbon atom is bonded to 4 nearest neighbors, forming a 3-dimensional lattice. These covalent bonds make carbon in the diamond form a network solid. Network solids are very hard and have high melting points.
Okay, so we just compared diamond and graphite, and diamond has this tetrahedral arrangement, which you should know what that looks like, of carbon atoms, whereas graphite has these layer of carbon atoms that are in rings. These layers can slide past each other. That's what makes graphite much weaker and slipperier. Think of your pencil lead. So here's our diamond, very complex, not going to slide past each other, but here's our graphite, layers upon layers, and they have this real weak, it says bonding, but really it's just this intermolecular force that's holding them together. Here's a picture of how their orbitals overlap. We have these p orbitals on the left that have this sp2 hybridization, and essentially what's happening here is these guys are all bonded up pretty strongly, and over here these guys can slide right past each other. So we will move on to molecular solids in the next video, and that will be the last one, I swear. See you soon.